For nearly 2,000 years, a dome has sat open to the sky in the middle of Rome, unreinforced, uncracked, and still the largest unreinforced concrete dome on Earth. When modern engineers first ran the numbers on the Pantheon's oculus and its coffered ceiling, the math kept coming back with the same uncomfortable answer. By the standards of contemporary concrete, this structure should not be standing. That contradiction is where this story begins. The Pantheon, as it stands today, was completed under the Emperor Hadrian around 125 AD. It replaced an earlier structure on the same site. The defining feature is a hemispherical dome roughly 43 meters in diameter, with a circular opening, the oculus, at its crown. No steel rebar runs through it. No post-tensioning cables hold it together. The Romans poured it, let it cure, and walked away. It has been in continuous use ever since, functioning today as a Catholic church. That is not a metaphor for Roman ambition. That is a documented engineering fact. To understand why this is remarkable, you need to understand what concrete actually does under load. Concrete is strong in compression. It handles weight pressing down on it very well. It is weak in tension. It resists being pulled apart poorly. A dome generates both. The upper portion is under compression, which concrete handles fine. But the lower portions, near the base, experience outward pushing tension forces called hoop stress. In a modern dome, steel reinforcement absorbs that tension. The Pantheon has none. So, how does it stand? The answer begins with the material itself. Roman concrete, known in Latin as Opus Caementicium, was not the same substance poured into modern buildings. Roman builders in the region around Rome had access to a volcanic ash called Pozzolana. When this ash was mixed with lime and water, it produced a hydraulic cement that could harden even in wet conditions and, critically, continued to strengthen over time through ongoing chemical reactions with its mineral environment. The sources confirm that Rome and its surrounding area contained various types of volcanic materials, which Romans experimented with extensively in the creation of building materials, particularly cements and mortars. This was not accidental discovery. It was the product of generations of material experimentation embedded in Roman construction practice. Roman architecture, as the sources document, moved from construction based on columns and lintels to one based on massive walls punctuated by arches and domes. That transition required solving structural problems that had no established precedent. The Romans achieved high levels of technology, in large part because they borrowed and then systematically improved upon techniques from the Greeks, Etruscans, and others. The Pantheon dome represents the culmination of that process, a structure where material science, geometry, and load management were integrated into a single coherent solution rather than treated as separate concerns. But the material alone does not explain the dome. The Romans also made a structural decision that was, by any measure, ingenious. They did not pour the same concrete from the base of the dome to the top. Instead, they varied the aggregate, the chunky filler material mixed into the concrete, as they built upward. Near the base, where loads are greatest, they used heavy, dense aggregate. As they moved higher toward the oculus, they progressively switched to lighter materials, eventually using pumice near the crown. Pumice is a volcanic rock so porous it can float on water. The result was a dome that became significantly lighter as it rose, reducing the tension forces at the base and shifting the overall stress distribution into a range the concrete could manage without reinforcement. The coffered ceiling, those recessed rectangular panels visible on the interior, was not purely decorative. Each coffer removed material from the dome's shell, reducing weight without sacrificing the structural geometry. The stepped rings visible on the exterior of the drum below the dome served a similar purpose, adding mass at the base to counteract outward thrust. Every visible feature of the Pantheon's design was doing structural work. The cost of this achievement was not trivial. Roman concrete construction on this scale required enormous organizational capacity, the ability to source specific volcanic materials, transport them to urban building sites, manage large labor forces, and maintain quality control across a structure being built in stages over years. The sources note that the Roman military was not only used for territorial acquisition and defense, but also assisted in construction projects. The infrastructure that made the Pantheon possible was itself a product of imperial-scale resource mobilization. A private builder in the ancient world could not have done this. It required the organizational machinery of empire. There is a legitimate counterpoint that needs to be addressed directly. Some researchers have noted that while Roman concrete's long-term durability is well documented, the precise chemical mechanisms are still being actively studied. The Pantheon's dome has survived, but it has also been maintained, repaired, and protected over 2 millennia. Attributing its survival entirely to the original material, without accounting for ongoing human intervention, would overstate the case. What the evidence supports is that the combination of material choice, aggregate grading, and geometric design produced a structure with exceptional longevity. Not that Roman concrete was universally superior to modern formulations in every application. What changed in our understanding is the direction of the question. For a long time, the Pantheon was treated as a mystery, an anomaly that defied explanation. The more productive framing, supported by the evidence, is that it was a solution. The Romans identified the constraints of their available materials, developed empirical knowledge of how those materials behaved, and designed around their limitations with enough precision that the result has outlasted virtually every structure built since. Roman architectural style continued to influence building in the former empire for many centuries, and the engineering principles embedded in structures like the Pantheon were gradually rediscovered and built upon during the Middle Ages and the beginning of the modern era. The sources are explicit that some of the more advanced concepts and inventions of Roman civilization were forgotten during the turbulent eras of late antiquity and the early Middle Ages, and that some feats of Roman civil engineering were not improved upon until the 19th century. The dome still stands open to the rain. Every time it rains in Rome, water falls through the oculus onto the slightly convex floor, drains through small holes in the marble, and disappears. The building handles it the same way it has handled everything else for 19 centuries, without complaint and without reinforcement. The question that follows naturally from this is not why the Romans could build this way, but why the knowledge was lost. The Pantheon did not fall. The civilization that built it did. And the gap between what was built and what came after is, in its own way, as striking as the dome itself. The next time you look at a modern concrete structure and wonder why it needs steel inside it, you are asking exactly the question Roman engineers already answered, and then the answer was forgotten for 1,000 years. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.